All right, so let's go over quiz 7 here. First problem, we're looking at the ring Z3 plus Z4. Part A, we want to list what are the units of this ring. So before I do that, let me just show you what it is we're trying to do. So we're looking at ordered pairs where the first coordinate comes from Z3, the second coordinate comes from Z4. And so what I need to do is be able to find something that multiplies by this ordered pair to give me the unity element, which is 1, 1. The multiplicative identity is 1, 1. So I need to have an inverse in both coordinates. A times A inverse would give me 1, B times B inverse would give me 1. So what I need to do is to have a unit in this direct sum, I need to have an invertible element in the first coordinate and an invertible element in the second coordinate. So let's think about these two rings separately first. In Z3, my three elements are 0, 1, and 2. 0 is never invertible, so we can forget that. 1 and 2 both have inverses. 1 times 1 is 1. 2 times 2 mod 3, that's also 1. So 1 and 2 are my invertible elements from Z3. In Z4, I have 0, 1, 2, and 3 as my potential elements. Again, 0 is not invertible, so we can throw that out. 1 is invertible. 1 times 1 is 1. 3 is invertible. 3 times 3 is 9, but mod 4, that's 1. So 1 and 3 are both invertible. 2 is not. 2 times anything, sorry. There is no multiplicative inverse for 2. And we know that because it's a factor of 4. It shares common factors with 4. In Zn, remember, Z in an element has a multiplicative inverse if it is relatively prime to the to the subscript. So 2 is not invertible. That means in my second coordinate I have to have a 1 or a 3. So my units in the direct sum are all the possible pairs where the first coordinate comes from 1 or 2, the second coordinate is 1 or 3. So if I list them, we've got 1, 1, 1, 3, 2, 1, and 2, 3. Any of these four pairs has a multiplicative inverse. All right, so those are the units. Then we've got zero divisors. This is the next question. Okay, so zero divisor in general is if I can find a pair of elements that multiply and give you 0, but each element is non-zero. So A and B can't be 0. So it's a factorization of 0 that does not involve 0. All right, so we're dealing with ordered pairs again. Remember when I was talking about zero divisors, if one of the coordinates is already 0, and the other coordinate is anything other than 0. So if the second coordinate was also 0, that would be a 0 element. That wouldn't be a zero divisor. If I have a pair like this, then what I can do is just in the second element, in the second pair, put a 0 in the opposite place and some non-zero thing in the first place. These will multiply to give me 0, 0. So we are looking for ordered pairs that I can find some other non-zero ordered pair that when I multiply them it gives me the 0 ordered pair. Okay, so this kind of construction will work. If one of the two coordinates is already 0, so 0, 1, 0, 2, and 0, 3, these will all be zero divisors because I can make up a corresponding element, the corresponding pair that will multiply with this to make both coordinates 0. So I could also put the 0 in the second place. So I could have 1, 0 or 2, 0. I don't have 3, 0 because this is Z3 in the first coordinate. So all of these are 0 divisors. But there's one more thing I can do. In Z4, I have a 0 divisor of 2. So in Z4, 2 times 2 equals 0. So if my second coordinate is 2, let me just illustrate with one of them. If my second coordinate is 2, I can kill off that coordinate with a 2 in my second pair. So in the second coordinate here, 2 times 2 would be 0. And then the first coordinate can be anything, because I'm free to put a 0 here. So if I put a 1 here, I can kill that off with a 0 without making the second pair fully 0. So 1, 2 times 0, 2 would give me 0, 2. So having a 2 in the second coordinate, that's also enough to make a 0 divisor. Okay, so 1, 2 works, and also 2, 2 works. So these are also 0 divisors in the direct sum. All right, so in general, the general rule for a situation like this is I produce a 0 divisor by either making one coordinate 0 and the other coordinate any non-zero element, or if there are 0 divisors in one of the individual rings, if I put a 0 divisor in that coordinate, that makes the whole ordered pair a 0 divisor. All right, so that's part B for 1. Okay, so 2 is asking for examples. So give an example of each of the following. Part A is asking for a finite non-commutative ring with characteristic 4. Okay, so if we want the characteristic of our ring to be 4, kind of our basic ring with characteristic 4 is Z4. That has characteristic 4. However, that's commutative. That's a commutative ring. Multiplication in Z4 is commutative. So what's my standard way to make a non-commutative ring is to take matrices. So I do M2 Z4. This would be 2 by 2 matrices, A, B, C, D, where all 4 of the entries come from Z4. So taking matrices will keep the same characteristic as whatever ring I'm using here. So this will be a characteristic 4 ring. It's non-commutative now because it's matrix multiplication. And it's still finite because there are 4 entries in each matrix, but for each entry I have a choice of 4 numbers. Each entry comes from Z4. So each entry is either 0, 1, 2, or 3. So there's going to be 4 to the 4th power matrices of this type. So it's finite. So that works. You could, the size of the matrix, once it's at least 2 by 2, it'll work. M3, Z4 would be a bigger example. But this does it. So then B is find an example of an infinite non-commutative ring with characteristic 4. Okay, so if I kind of have to do the same thing. I want to start with Z4. That gives me characteristic 4. I want to take matrices. That gives me non-commutative. But that's finite if that's all I do. So what I can do is, before I take the matrix, let's do an infinite. Let's turn this into an infinite ring while still maintaining the characteristic. One way of doing that is, if I've got a ring, if I have a finite ring, I can make an infinite ring by making polynomials, taking polynomials with those coefficients. So these are Z4 polynomials. Polynomials with Z4 coefficients. It's still commutative at this point. It still has characteristic 4. If I want to make it non-commutative, I take matrices of this. So these are matrices where 2 by 2 matrices where each of the 4 entries is a Z4 polynomial. And now there are infinitely many polynomials I can put into each of these slots. So this will be an infinite ring. It's non-commutative because it's matrix multiplication. And it's characteristic 4 because Z4 had characteristic 4. Taking polynomial rings maintains the same characteristic. Taking matrices maintains the same characteristic. So these will be characteristic 4. It's a characteristic 4 ring. All right. Finally, number 3, we have a proof. D is an integral domain. Suppose a squared equals a for some a and d. We want to prove a equals 0 or a equals 1. So this was a problem in the homework list, I believe. It was fancied up a little bit by referring to idempotence, but you don't have to memorize the definition of idempotent. In any case, we could prove this by appealing to the cancellation property in integral domains. Let me avoid that though and just do it directly. So here's our proof. Suppose we've got a squared equals a. I don't have a inverse. We don't have inverses under multiplication necessarily. What I can do though is I can subtract. So I can subtract a from both sides. And then I can always factor out common factors. So I have the distributive property. And so as long as we have a unity element, as long as we have a 1 element, if I have a here, I can pull out an a and that leaves me with a 1. So I can factor out an a, leaving me with a minus 1. I can only do this because I'm in an integral domain and there is a 1. Integral domains are commutative rings with unity, with an extra property, but they have a unity, so I have a 1 that gets left over. So a times a minus 1 equals 0. And then my next step, this is the key step in this proof. In an integral domain, if 0 factors, if we have factorization of 0, so a product equals 0, that means one of the factors in my product equals 0 already. So since D is an integral domain, either a equals 0 or a minus 1 equals 0. And if a minus 1 equals 0, that means a equals 1 because I can add 1 to both sides. So a equals 0 or a equals 1, and we're done. All right, so that's it for quiz 7, right? Yeah. So if you have other questions or need more clarification on any of these problems, send me an email and I'll answer as best I can. Or as usual, we can always schedule a Zoom meeting or something else if that doesn't work for you. All right, so that's it.